So hi everyone. As Mark suggested, the work we're doing is in Saline Rangelands. So what I'll present today is a series of experimental work that we've been conducting in Saline Rangelands to address both sediment transports as well as salt transports to surface water systems. I'd like to acknowledge my co-authors for this work. There's Dr. Welts from ARS and Ken McGuire from the Desert Research Institute. And I'll also spend perhaps a few seconds to acknowledge my some of the funding agencies that supported us. There's the BLM, the BOR, and we also got a strong support from the Colorado River Salinity Forum. I would also like to talk about some of the people who have supported us technically and logistically, and I would like to mention a few names: Desandra Lee and Todd Adams, and many more people that are associated with this work. People on the in BLM field offices, Ahmed Mohsen in Price, Utah, and even private range managers, Jim Fover in this particular case. A quick background, why are we doing this work? People think of these saline rangelands usually, and you'll see some of the pictures, they look very desolate, they're arid or semi-arid on the very low precipitation regimes. And so people usually wonder why does it matter to really look at erosion and hydrology in those areas? And a quick answer would be, well, it doesn't rain very often there, but when it does, it's usually large storms, and that is usually associated with a lot of solute transport in water that managers have to deal with downstream. So the Colorado River, not unknown to most people here, it drains a pretty significantly large basin. It's 242,000 square miles, and it's a major economic and cultural resource for many southwestern states. It's used for municipal water by about 40 million people in the basin state and many more in Mexico. And it's also an essential resource for many Native American tribes. And it's also used for agricultural purposes. Irrigation is irrigating about more than 5 million acres in U.S. and more in Mexico, and it was also used for also has other uses, namely wildlife, refuge, recreation, hydropowers, and all sorts of many other uses. So the salt problem in the Colorado River when you look at the river, doesn't seem that obvious, but when you start looking at the numbers, at Hoover Dam, the annual salt load is estimated to about 9 million tons. So that's 9 million tons per year that is passing through at Hoover Dam, and is associated that amount of salt is associated with cost. It's associated with a real cost, currently estimated to about $300 million a year, and is projected to rise by 2030 to a significant number. And historical concerns in the river about the salinity led to the creation of management and coordination agencies, including the Salinity Forum, and that forum currently set a goal to reduce salt delivery to the river by about more than 600 tons. his previous research in basin have identified a significant portion of the salt delivered to the river coming from natural ranges, natural processes. And that includes saline springs, groundwater discharge, erosion, evaporation, and so on. And a significant portion of that natural salinity is actually coming from natural rangelands. And in these rangelands, the salt is occurring because of the marine parent material that from which the soil is derived. So the knowledge gaps that we're trying to address here relate to the rainfall-driven transport and erosion mechanism. Particularly, we're trying to better understand how the high salt content might influence the erodibility. So some of the properties and parameters that Sam just talked about, the assumption here is that they might be influenced significantly by the level of salt in those formations. And we also, when you look at the map that both Sam and Mariano showed about where the data was collected to develop some of the equations that are used in RAM, WEP, and a lot of other process-based model, not very many, and I can say with pretty good confidence that not very many sites came from those saline rangelands. And matter of fact, it seems like the only site that was in the data set was thrown out because it was behaving completely differently. Right now we have a great opportunity to really address some of those rangelands. So our objectives here is to quantify the amount of salt transport that we have from these rangelands during rainfall-driven processes, and develop salinity-dependent erosion equations, improve our understanding of sediment transport processes as they are affected by other biotic and abiotic processes. And so all this, to summarize all of this, how did we go by in this work? We essentially designed rainfall simulation experiments in these rangelands to probe the landscape and see how much salt and sediment is being transported during rainfalls. To give you an idea of what the landscape looks like, I put that picture there. They look very barren. There's not very much vegetation, and so what we have in that picture is our rainfall simulator set up with our crew working during a rainfall simulation experiment there. So our experimental design, we have an experimental design. Our simulation plots are essentially 6 meter by 2 meter wide. They are smaller than the traditional web era rainfall simulation plots. We had 4 rainfall intensities that we experimented, and those intensities were developed, were calculated based on the historical precipitation record. So we used the NOAA Atlas 14 estimates for rainfall intensity to derive these intensities. And so the intensities are applied with our simulator, and we have a computer control simulator that allows us to set an intensity and run a simulation at that intensity pretty precisely. And each intensity, because we're looking at the transport of salt, we didn't want to have a legacy effect of treatment on each plot. So each plot was used only once because we didn't want to remove too much salt from one event and then reapply on it. So to avoid those confounding factors, we decided to have one single intensity per plot. So 3 replicates per intensity, and that led us to, per site, we end up with 12 plots. Currently we have data from 2 sites, so a total of 24 plots, and there's many 2 or 3 more to come in this setting. We have runoff and sediment concentration measurement. We measure it in this supercritical flume here. We have a series, actually a lot of sensors that are essentially either measuring the discharge, so that during a run we have a high temporal resolution in our hydrograph, and we also collect sediment samples as well as water quality samples. But my talk today is not going to present any of that data. That will be Dr. Welt's, the content of Dr. Welt's talk. So we collect runoff and sediment concentration data, and as you know, this hydrograph and sedograph shows you what a run looks like. It's classical rainfall simulation experiment. You have an initial increase in sediment concentration and then a drop over time. You know, that Sam just presented as the exponential decay. We also have designed these salt sensors. They're wireless salt sensors. They form a wireless network to essentially monitor the salinity of the runoff during a rainfall event, and that allows us, that those sensors are used for more than one purpose. In this particular setting, we're using them essentially to just look at the dynamic of the salt transport during a rainfall. And the hope was that there's a process called efflorescence that we read about a lot, by which there's essentially a seepage of super concentrated fluid from the soil to the surface, and during evaporation we have the salt that crystallizes at the surface and then creates that salt crust. And the thought was that if there's such process, we should be able to pick up that response in with these electrical resistance probes. But that data has not been looked at yet. And so what I'll present today is actually data from something that we added to the whole work, and an additional technology that we added. And the goal here is actually to address a lot of the sediment transport and soil erosion questions that were historically extremely difficult to address. But here we have a unique opportunity, and we decided to grab that opportunity and equip our simulator with extra technologies. Here what I'm showing you is a camera that we use to take overlapping pictures of the plot before and after rain, and that allows us to recreate the surface microtopography at very fine resolution, sub-millimeter resolution. And in the next few slides, I'll show you, the kind of things that we can really do with that data. And it's based on a technology called structure from motion. It's essentially a synonym to photogrammetry, measuring surfaces with pictures. So with that, we can track erosion and deposition patterns independently, and that has significant advantage for soil erosion work. So this is an example of a surface reconstruction with this technology. You have a synoptic view of the plot here. I don't know if you can see them, but you can essentially see, you can identify some of those isolated shrubs and then the soil surface. And with this series of pictures that I was talking about, you can reconstruct the soil microtopography. This figure here shows you the a DEM of the soil surface. This DEM is at a resolution about 1 millimeter, and what it shows you is a DEM before an event and after the event, after a 25-year storm, and you can clearly identify some of the cuts that was formed. You can see the smoothing of the surface. You know, those holes that you see there, they're actually cow hoof prints that were erased. So essentially filled in during the rainfall, and you can clearly identify the flow network. And why are we doing, my presentation is going to focus a little bit on that, on data that we collect with that technology. And why is that? If you remember, Sam's paper, Sam's talk really talked about the distinction between sheet and splash erosion, concentrated flow erosion. There's also the concept of transport, which on rangelands has a tremendous implication, a very significant implication. Transport is associated with the concept of resource redistribution, downslope. And if we remember, Jason's presentation was talking about how as you start increasing the slope length, the size of your plot, you start running into scale issues where the amount of sediment delivery does not simply scale to what you observe at a much finer resolution. So with this technology now, we can start looking at more precisely in a spatially distributed fashion what is happening on the surface during a rainstorm. How, if you see what is in purple there is erosion pathways. How are those erosion pathways defined by the presence of shrubs? All the little white gaps that you see, they're little shrub clumps that were removed from the reconstruction. But I don't know if I mentioned it, I probably did not. What you see here is simply a DEM of a difference of DEM. So you take the DEM before, you take the DEM after, and from that difference you can essentially identify areas that were eroded, so erosion pixels, and deposition pixel, areas that received some sediment, and areas that essentially did not change significantly. And what that allows you to do is parse out erosion from deposition processes and also identify areas that were under just diffuse processes or sheet and splash in this case. So again, for each plot we have before after event DEMs, and then that allows us to have a DEM of differences that allow us to characterize the surface and take that surface characteristics now to link to hydrology and so the runoff and soil loss data that we collected. So we have two independent data to really try to understand what is happening at the soil surface. So from each DEM, so from each surface analysis, we developed a series of parameters or I'll say metrics to really represent different surface processes. And the surface processes that we are trying to target are overall erosion and deposition. So the net erosion and deposition that you collect in your sediment bottle at the bottom of your plot, as well as more specific processes such as concentrated flow erosion and sheet and splash erosion, areas that did not concentrate flow, and also deposition. And this is a very interesting one. If you look at soil erosion research historically, it's extremely difficult to quantify deposition because there's often no way to measure it experimentally in the field. So right now we have this technology that allows us to start addressing some of these okay. So in the next series of slides, I'll show you some preliminary data to really give you an idea of what we can do with that data and what we plan, what we intend to do with that data. Some of the metrics that we developed, wherever you see TVE is the total volume of erosion. So if you take each DEM, you subtract DEM before and after, you get an idea of the total erosion that occurred. So all the pixels that lost some height, you can add them up and have a number, and you can do the same thing with deposition pixels, and then you can, for each plot you have one value. So each of these dots is the value for a single plot, and then in the x-axis, you can then put in some of the hydrology or erosion information that we have. And the point of this slide is to show that by adding, I think I skipped one, yeah. The point of this slide here is showing that by adding the depth information, so by considering the elevation change, we essentially improve significantly the correlation between observed soil loss or sediment or runoff and the surface characteristics. So the left graph does not contain any depth information. We're just looking at the area, the number of pixels essentially that have lost or gained elevation. And in the right, we essentially account for the depth information. Next slide. Here I'm quickly showing something interesting that we're finding out is that the surface change that we observe with the 3D is actually more explained by runoff, so hydrology processes, than soil loss, which is counterintuitive. But what we believe is happening is that the colloids, so the very small fraction of the soil loss, does not really contribute that much to the surface change that we observed. And this is what I was mentioning. We can really separate erosion in channels so the concentrated flow pathways from the total erosion, and then start looking at the relationship between those concentrated flow processes and runoff and soil loss. And here we're showing that there seems to be an equilibrium between the network that is formed and the hydrology. And the reason for that is that when we take the cumulative runoff, we plot the cumulative runoff versus the total erosion volume in the channels, the prediction is worse than when we only consider the runoff rate. And we can also derive some ratios to really look at some more specific hydraulic parameters. For example, the reel width over reel spacing, which is often really used in some soil erosion models, process-based models. We can derive that and using this data. And to go quickly, the left side is showing essentially on a single plot what's the proportion of concentrated flow that is occurring with respect to the total erosion. And we can also look at the energy expenditure on the surface, essentially by how much does the network expand in relation to runoff or slope. And so I'll just go quickly over these parameters. The point here is to show that we can look at the surface change and relate that to hydrology and erosion information. And we can also start looking at more specifically some of the equations that were developed. Sam just presented one. We evaluate some of these equations and see whether we can improve our understanding of these erosion processes. We can get channel weights, we can segment the surfaces out and try to define now some more advanced ways to get channel network characteristics. So this is saying the same thing we can get in the channel network. So the delineated areas of the channel networks, we can get our we can test our concentrated flow erosion equations in those areas and test in the other areas the sheet and splash erosion equations. And we can also look at the influence of shrubs, the distribution of shrubs on soil loss, on sediment. Here is a quick conceptual model on how we're going to approach that. If we take a single shrub and a radius around that shrub, an increasing radius around that shrub, then we'll hypothetically reach a point where the erosion minus deposition will be greater than 0, in which case we will be under degradation conditions. So those are just some quick slides to show you what we can do with that data. Dr. Wells will present some of the findings that some of the soil loss and water quality data. So to quickly conclude, this work in this very barren landscapes offer now an opportunity to really look at the sediment transport processes in a very novel way. And that's what I was trying to share today. Thank you.